Okay, now the next rule that we're going to discuss is the chain rule. And this is perhaps one of the most important rules as far as advanced differentiation goes. And the reason for that is very often uh, things don't necessarily change because of only one other thing changing. They quite often in real life change because multiple things are changing or causing other things themselves to change. And so rather than consider all of them individually, we're going to look at all of them at once. And so this is what the chain rule says. Let y be a function of some other function u, and let that be differentiable, a differentiable function of u, and let u also be differentiable function but of x. So then the function y is the composite, or f of g of x. The function y is f of g of x is a differentiable function of x. And so now what we're doing is we're embedding functions. So rather than being able, they're having to look at functions as far as being multiplied or divided or added or subtracted, we are now looking at functions of functions. So this is one way to write the chain rule. This is a very nice way to write it when you're talking about related rates and trying to figure out how quickly something is changing. It's a very useful way to describe that. However, in practice, it is much easier to use this equivalent form. And the way that that I was taught, and this is a great way for me. If you look at it, it's the derivative of the outside times the derivative of the inside. Okay, and so let's take a couple of examples here. So let's say we have something like y is equal to the square root of x squared plus 1. Okay, and we're told to find the derivative of that. Well, we can rewrite this as y equals the quantity x squared plus 1 raised to the 1/2 power. So now if I allow the inside thing to be g of x is equal to x squared plus 1, and I allow u to equal to x squared plus 1, then y is equal to u to the 1/2. According to the chain rule, I take the derivative of y with respect to u. Okay? So the very first thing I have to do is take the derivative of y with respect to u. The derivative of y with respect to u is equal to 1/2 u to the negative 1/2 through the use of the power rule. Or that's 1 over 2 square roots of u. Now keep in mind, u is actually x squared plus 1. So if I take that and I substitute that in for u down here, then what I get is I get that the derivative of y with respect to u is equal to 1 over 2 times the square root of x squared plus 1. Well, that's dy du. We have that. Okay, now we need du dx. So now what we need to do is we need to find what is u prime, or the first derivative of g of x. So du dx is equal to the derivative of x squared, which is 2x, and then the derivative of 1 is 0. And so the du dx is 2x. According to the chain rule then, I multiply those two derivatives. And so by combining them, dy over derivative of y with respect to u times the derivative of u with respect to x is equal to 2x, so this part is 2x, the du dx part, 2x times 1 is 2x, divided by 2 root x squared plus 1. All right, So now, after all of that, we found that y prime then is equal to 2x over 2 times the square root of x squared plus 1. That's for example. Now, trick. We used the top the top relation between the derivative and the chain rule. Now we're going to utilize the bottom, and we're going to do the same problem. Okay, so let me go ahead and repeat this down here, where I've got y prime is equal to f prime of g of x times g prime of x. Okay, recall that y is equal to the square root of x squared plus 1. Okay, now to start off, I'm going to rewrite this the same way I did the other, as y is equal to x squared minus or plus 1 raised to the 1/2. So the way to utilize this, the derivative of y with respect to x is the derivative of the outside, which is 1/2 x squared plus 1 to the negative 1/2. Okay, times the derivative of what's inside, which is 2x. And so y prime is then equal to 2x times 1, which is 2x, over 2 times the square root of x squared plus 1. The negative tells us to flip it to the bottom. The 1/2 gives us our square root. So in practice, if you're simply just taking a derivative, then the way of using this form here, where you're taking the derivative of the outside times the derivative of the inside, is a much easier and useful method. If, however, you are solving an actual problem, and when we get into related rates, you'll see this come into play. But if you're trying to solve an actual problem where you have two things that are changing, very often you have the rate of change of one of these. And so using this format, this du or dy du times du dx, that format actually tends to work better. So to take a derivative, it's easier to use the second format. To utilize the derivative in a problem, it's easier for the first format. At least I found that to be true for me. All right, that's the chain rule. Let's do a few examples.